Hi, my name is Juan Cota, and this is the presentation for my final project in digital forensics. Let's begin. For our final project, we were told to go to a website in our domain and select an article to do a research project over. The article that I have chosen is Identifying Document Similarity Using a Fast Estimation of the Levenshtein Edit Distance Based on Compression and Signatures. The authors of this article were Peter Coates and Frank Breitinger. The problem that was being addressed in this article is the identification of relevant artifacts. On any operating system or any computer, there are several files. Executable files, text files, document files, configuration files, just several files. And one of the hardest things to do is being able to identify what a relevant artifact or a relevant piece of information is. Oftentimes, the way that this is done is by using file hashing and whitelist and blacklist. To do this, basically, an investigator will take and they will find an exact replica or the base starting point of a operating system. And so, say for example, I have an operating system that's running Red Hat Enterprise Linux 7.5. And to investigate into this operating system, basically what I'm going to do is get an exact replica or find a source of trusted sources. I'm going to hash all of those files and put them into a list. Then what I'm going to do is I'm going to take and go to my target, and I'm going to hash all the files on target, and then I'm going to try to match those hashes to the hashes from my trusted source. And if those hashes match, then the artifact is irrelevant to me. If the hashes do not match, then the artifact is relevant to me, and I'm going to want to investigate it further. For a blacklist, what I'm going to do is I'm going to take and I'm going to have some type of malicious file, malicious code, or item of interest, article of interest. I'm going to take a hash of that article of interest, and then I'm going to scan my target to see if I can find a file that has a hash that matches. Now, the weakness with this is that the hash has to match, and hashing will only match identical artifacts. So if an artifact is not identical, then the hash isn't going to match, which means it will not be identified properly. All right? To overcome this problem, investigators have come up with methodologies of approximate matching. So they use similarity hashing or fuzzy hashing, and this gives a certainty score that they use. They set a threshold, and they set that threshold, and they say, hey, well, the certainty score is above this threshold, so this is an item of interest. We're going to save that for later, and we'll investigate into it, therefore identifying an artifact of interest. But this normally works best with larger files, and most of the files on an operating system are not larger files. So, addressed in the abstract is the identification of document similarity has many applications, on and on, source code analysis, plagiarism detection. But the problem with this is that, one, they have to be an exact match, and anybody that's ever done any type of plagiarism or copied somebody's homework knows, hey, guess what? I'm not going to copy it word for word. I'm going to make it similar so I can bypass the idea of somebody being able to search for it, and there you go. But one of the things that can be done is using the Levenshtein Edit Distance to then try to compare these two documents and see if they're similar and if they're not similar. But using the Levenshtein Edit Distance works best on files that are not medium to large. So if I have, let's say, 500,000 lines of source code, Levenshtein Edit Distance isn't going to work on that because it's a quadratic formula, meaning that the time it would take to run this algorithm on all of that code would be not good and basically make it just not what you want to do. So what the authors are proposing here is that they use they compress the data and they get this keyhole signature through a compression algorithm, and then they perform the Levenshtein Edit Distance on that compression or that file signature. All right, and of course, in the abstract it says, hey, we showed promising results, because why would they say anything else? So let's continue on and figure out what's going on and if it's worth our time. So their solution was that, hey, we're going to compress this thing, we're going to use Levenshtein edit distance, and we want it to be under 30,000 units of measure. Anything over 30,000 units of measure, trying to compare a two-dimensional array of 30,000 and 30,000 gets to be a bit resource-consuming on your computer. But either way, let's go into the methodologies of what they used. All right. So the methodologies basically that they're using on these files are as follows. First, we have the Levenshtein distance. Now, the Levenshtein distance basically is a calculation to determine how much it's going to take to turn one word into another word. So form to fork, kitten to sitting, abacadabra to abracadabra. So if we look at the first example here, we see that to take and turn the word form into fork, what we'll need to do is we'll need to substitute that M with a K. So for this specific example, all we have to do is perform one substitution, so we have a 1. Just a little side note that that 1 is editable to be something else. I'll explain that here in a minute. For our second example, we have the idea of taking the word kitten to sitting. All right. So if we look at the first word, or the first set here, right up here, the idea is that we're going to substitute the K for an S. All right. And then we keep going and we iterate over the first iteration, take the K to an S, second iteration, I as an I, T as T, E as an E, N as an N, or E is an, I need to change the E to an I. So basically here's where I'd substitute the E for an I, and then we have an N, and then we get to our final stage where we need to add a G. All right. So in this case, we have 2 substitution and 1 insertion or addition, which would make the edit distance a 3. So with these things in mind, basically what we have here is the equation that basically states, hey, if I am going to substitute, it's a value of 1. If I'm going to add, it's a value of 1. If I'm going to subtract, it's a value of 1, da 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 da. One thing to note here is that these values of 1 are editable. This value, and this value. And the reason being is because basically the idea behind the algorithm is that we need to look at the results and then target the algorithm to then match the results that we're trying to make on a control set. All right? So one of the main proponents of this is that if, let's say, we get rid of substitution, what's the value? Well, to actually substitute, I have to delete a character and then add a character. So in some cases, some instances, the substitution method is then replaced with a value of 2 instead of a value of 1 because the value of 2, because I had to remove and then add. But that's a different story. Now, what they do to perform an Levenshtein edit distance is usually they'll create a 2-dimensional array. So for our third example, we have taking the word abacadabra to abracadabra. All right, and we create this 2-dimensional array, and we start out with, okay, I'm an absolute 0 here. And if I'm an absolute 0, then I have to add an A, add a B, B, A, C, A, D, B, B, A. Right? So if I had nothing and I wanted to see the Levenshtein edit distance of taking nothing to abacadabra, it would be a 10. If I had an A and I wanted to take it to abacadabra, it would be a 9. So you can see the pattern, and if we look at the end result here, we see that the end result is a 3. Well, also looking at this, we can also see and determine why that if I had 30,000 characters or more, it would be quite costly in memory to try to create a 30,000 by 30,000 array and then try to match and perform mathematical calculations on this. So the next idea that we had to, or that was addressed in the article, is the compression mechanism, which needs to be performed on this set of data. Now, there are 2 forms of compression. 1 is lossless and 2 is lossy. So as lossless compression is the standard type of compression that we think of when I'm going to compress a set of files. I have a file and I want to zip it up and I want to send it over to another computer. Well, the idea behind that is that I'm able to come back from that I am able to take this set of files, this set of movies or DVDs or music files, I can compress them down into a 2 gigabyte DVD drive, and then I can take it wherever I want, and then I can decompress it, and it's still the same. But for the purposes of this article, they chose to go with a lossy compression because, number one, you can compress greater. You don't have to keep the original data. And number two, one of the other purposes that will be explained later and seen in the purposes of the article is for the purpose of anonymous searching. So they chose to go with a lossy compression mechanism. Now, the rules for this compression are as follows. Compression. The digest must be much smaller than the original input, where much is a factor of low to high, of hundreds to low thousands. It also must be deterministic, which means that the digest must be identical for identical inputs. Right? So if I throw in ABC, I get a digest of XYZ, then if I do it again, it's still going to come out with XYZ, no matter how many times I run it. 1 time, 1,000 times, 1,000,000 times. If I put in ABC, I'm getting XYZ out. All right? Now, the fourth one is runtime efficiency. Ideally, the compression algorithm runs in a linear time with respect to the length of the input. All right? We'll get into that one in a minute, because that was the determining factor of why they used the algorithm that they did. But the fourth one, or fifth one down there, or fourth one, is the result of concatenation of the digest of 2 strings shall be identical to the concatenation of 2 strings and then performing a digest function. Now, for the purposes of this article, the algorithm that the author selected does not actually meet this requirement, but is considered good enough. And if they consider it good enough, I'm going to consider it good enough, and we'll just run with it and see what we find. All right? Carrying on. The authors decided to use the Rabin-Karp algorithm. Now, this is a fun one because they call it the Rabin-Karp algorithm, but it happens sometimes. So the idea behind the Rabin-Karp algorithm is that what they're going to do is that they are going to take the neighborhood size of the data string, and then they're going to try to compress it, and they're going to basically go through digest alphabet, and we'll just walk through this right quick, right? So let's say I have a neighborhood of 3, because the Rabin-Karp algorithm was originally the Rabin-Karp search algorithm, where I'm going to search for a pattern, and the pattern length was the original neighborhood. So let's say we have a pattern length of 3, and I want to search through this string to see if a pattern matches. Gives us the reason why we have the neighborhood length. Anyway, so we take this neighborhood, and then the first idea is to assign each character a value. For the alphabet, or the alphabet that we're using, we're only using A through J, which is the numbers 1 through 10. And if we look at this example here, it says that, okay, I have, in my neighborhood, I have the first 3 characters as C, C, and A. So C has a value of 3, C has a value of 3, A has a value of 3. Therefore, when you add them together, we get a 7. All right, cool. But the problem with this is, if I add, let's say like at the end here, we have a D, B, and an A, you add those 3 together, you get a 7 as well. So how do we get around this problem? Well, let's just take and see if we can do that. And the idea here was that they're going to take the 3, add them together, and multiply by the size of the alphabet raised to the exponent of the pattern length minus 1 of whatever entity in the pattern that they are on, as can be seen in this nice little example here. this gets fun. So basically, when you take 3, 3, and 1, you get 331. Whereas when you take 4, 2, and 7, which is D, B, and A, you get 421. Now the values are no longer the same, and we're good. All right? So that's where we get this whole nice little piece down here. But there's a problem when we actually go into a larger neighborhood. Let's say we take that neighborhood size and upgrade it to 7. And let's say we're using all, ASCII characters. So the ASCII alphabet is 256. So now you have 256 to whatever neighborhood size. So if we have a neighborhood size of 7, you have 256 raised to the power of 7, or 10, or 12, or 25. The problem then becomes when you raise 256 to some very large power like that, well, you get an integer overflow. Unless you're using Python, but that's a different story. So one of the other things that they have done that helps pull it all together is that they use modulo math. But I'm getting ahead of myself. So in this idea of using modulo math, not only to keep us from going into integer overflow, we can also use integer or modulo math to then perform a rolling hash instead of an actual hash. So if we go back to here and we look at this, normally we would say, hey, I'm going to take these first 3 right here, and I'm going to perform my hashing algorithm. Then I'm going to take these next 3, and then I'm going to perform my hashing algorithm. And then I'm going to take these next 3, and then I'm going to perform my hashing algorithm. But with modulo math, I can take these first 3, perform my hashing algorithm, and then subtract the first one, and then add the next one, and then perform my hashing algorithm through some very interesting math that sometimes makes sense and sometimes it doesn't. But I digress. The purpose of this is actually that the average best case of the complexity for the Raven-Karp algorithm is O of m plus n. And the worst case jumps up to O m times n. But using modulo math and the rolling hash, we take that O of mn and reduce it to O of m. Hey, this works really great when you're trying to do something that is over 500 megs. Because when you do something, over 500 megs, it sounds like your computer's about to take off and go to Mars. But anyway, so what I have here in this slide is my personal implementation of the Raven-Karp algorithms used to perform a hashing digest of a data set. All right? So the things that we're going to need to know here is n, size of the neighborhood. All right? So since we're not actually comparing from one string to another, now we actually have to define a neighborhood size. All right? Next thing we need to know is our alphabet. This is our input character set. So this is the alphabet of anything that can be put into this bleeding thing. All right? So for this specific one, I chose any printable string because, hey, if it can go in a document, it's printable. So I'm taking it. All right? Next, we need to have the data from wherever. So basically, we target a file, I pull in data. That's the data, or self.data, as explained here. C, self.c, is the compression rate. This is pretty much needs to be a prime number. It's not necessarily required. I haven't done enough testing to give you a for sure answer on that, but that's okay. It's usually a prime number. We're going to stick with prime number. I like it. It's going to work. All right. And the last piece that I need to know in this is the digest alphabet. This is the character set that I'm going to use to create my digest. This I have specifically chosen, and the author specifically chose, because when we're creating a signature for a file, does us no good if that signature contains a character that is used as a delimiter in the file signature. So basically, the authors had specified in the paper that this is the character set that they are using for the digest alphabet, whereas I am going to use the same one, but for the alphabet of any character that can be input, I'm going to use the printable characters as listed in the string package that is provided with Python, whatever version you want to use of Python. All right? Now, if you look at this, We go back in and we have the original hash, which is right here. We have all sorts of fun stuff, and it basically comes out with a hash. All right. Now, the last piece and the last methodology of things we need to know is that we need to create a file signature. All right. And this signature is basically, hey, man, I'm going to have specific pieces of information so that I can just give you this piece of information so you don't have to recalculate it, and then you can go do your own stuff. Hence, also playing into the anonymous search portion that we'll discuss eventually. But for the file signature, basically what is provided is the file path and the name of the original file, the length of the original file, or the length of the data that is in that file, all right? C, the compression that is used to generate the signature, and the neighborhood that is used to generate the signature, the length of the digest, and the digest itself, or LCA digest, which stands for the Lossy Compression Algorithm Digest. Now, there are only two parts that are actually required by their definition, which is the length of the original file and the LCA digest. But in all the ones that I've created, I just decided to go ahead and throw them all in there. Why? Because I do it programmatically, and hey, more information is usually better. So, carrying on, let's see some examples of this wonderful, wonderful algorithm. All right. So, if we look here, basically, this is the output of the code that I created to put all this fun stuff together. And I have two files. File number 1 is named alpha1.txt. File 2 is alpha2.txt. File 1 contains the alphabetical characters A through Z, all uppercase. Alpha2.txt contains A through Z, all uppercase, and A through Z, all lowercase. All right. So, in this information that is output, you see the file name, which is alpha1.txt. The file path, and it's basically where I stored this file. The file size, which was the size of the file that is read by the file system. The compression rate, which in this one I used a compression rate of 3, and I use a neighborhood size of 5. The length of the data read from the file is 27 for alpha 1 and 53 for alpha 2. And as you can see here, the digest created is this nice little string of numbers and letters and characters, or whatever we call them. And then you see the generated file signature. This is that wonderful part that comes to the end of all this fun stuff of what they tested and generated. All right. So, carrying on, I'm going to use the same two files, but I'm going to use some different values just because, I can. And this is where I used a compression rate of 3 and a neighborhood of 7. All right, so that means when we ran this, the neighborhood size was 1, 2, 3, 4, 5, 6, 7. So A through G. And then the second was B through H. And the third was C through I. And we take all that, we put it together, we do the modulo math, and out pops these nice little file digests. All right. So now let's go into what we can use this for. All right. We can use this specifically for source code analysis, plagiarism detection, fuzzy string matching. Basically, searching a document to see if the characters in this one are similar to the characters in that one. Okay, I get it, but there are other tools that do very similar stuff to this. The one that really sparked my curiosity was the anonymous searching. Now, that one actually warms the deepest, darkest parts of my heart, because now I don't have to provide files for somebody to search. So with the idea of going to cloud computing and distributed computing, I don't actually have to perform these analysis of specific things on my computer. I can send a list of hashes out to the wonderful worldwide cloud, and the mathematical computations can be done by very, very large computers with ungodly amounts of RAM, and they can send me the results. But I don't have to send them my actual data. I just have to send them a hash. See, if we look back and we go back to this nice little slide before, we can see here that there's pretty much no way they're going back from A, B, C, D, A through Z from this nice little string right here or this nice little string right here. There are too many collisions possible when you use a large data set to go back. One of the ways you can actually think about this is that, the government standards for a password are a specific number of length, right? These are the guys that are supposed to know everything about security in the entire world, and they're top of the top. And they say, hey, today your password must be 16 characters long. All right, well, at this point, my password is 27 characters long. Go back from this. And you can, but not very well, and it's going to take some computation. Hey, that's all well and good, but in some further examples, you'll see we're up to 50,000 characters. You're not coming back from that. Or you might. Prove me wrong. So, examples of basically comparing two files to each other, all right? So the authors wanted to compare these two files to each other, and they wanted to be able to compare the hashing mechanism and then perform the Levenshtein edit distance of two files. So basically, these guys, they published some source code, and in the source code, they had some documents, and those documents were the test file they used. So I just decided to take those and have some fun with them. And these are the files, and specifically, what I'm doing here is comparing XAB-control to XAB2, all right? And in this, you can see that the file names are XAB-control and XAB2, that the file path is at that file path of wherever I store it. The file size is 22, for file 1 is 22.68 kilobytes, for file 2 is 24.38 kilobytes. The compression rate I'm using is 101, all right? The length of digest of file 1 is 278 characters. The length of digest from file 2 is 300 and yada, 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 yada. Length of data, 23,000, 25,000. The Levenshtein edit distance from the digest, file digest 1, to file digest 2 is 48. All right? And if you look at file digest 1 and file digest 2, you can see, hey man, these are actually pretty similar. Not only are they similar, you can see that the only change is really here at the end here, where they just decided to add some baloney. But with the Levenshtein distance of the digest, they run it through some other mathematical calculations that are documented in the article to create what they say is the estimated Levenshtein edit distance. So the estimated Levenshtein edit distance that they are calculating is that there are 1,734 edits needed to change the 23,226 characters to the 24,960 characters in file 2. As well, they say that the significance score that they have is a 1, and as you can see, they're actually pretty similar, except for this nice little string at the end. And also that you have the file signature for file 1, which contains the file path, length of the data, compression rate, neighborhood size, digest length, and then the digest itself. Also, we see that the character that they use as a delimiter is the comma. So that couldn't be one of the characters in our digest alphabet. All right, so what we have here is one of the examples. Now let's go to the next one. I also did this again on another two files they had, XAS-control and XAX1. And as you can see here, first one was 25K, second one was 25.7K, compression rate of 101, digest, the difference in digest is 6 characters here, so there's from 249 to 255, and the length of the data, you have the Levenshtein distance of the digest, you have the estimated Levenshtein distance, and you have the significance score. All right. So the significance score here was a 0.95, saying, hey, they're similar, but there's something different. And we can actually look through the digest because these are actually quite small, and we can see, hey, there's some differences. If we look here, we have that :1, we have a :1, FS plus da-da-da. Hey, look, I got this little stuff right here. No, that's not it. But anyway, you can look through there and you can see that there's actually some differences. All right. So that was basically the main meat and potatoes of the article that they were presenting. And then they went through and they ran it a whole bunch of times on a whole bunch of different files and got some file times, and it actually does show improvement. you don't really need to see the tables to know that it shows improvement. Because if you tried to run a Levenshtein edit distance on something that was 25K, your computer would sound like it was built by Elon Musk taking off for Mars, right? The fact that I can run this means that, yeah, significant improvement. The next fact is that I can actually throw this in a visual tool, look at it, and see the differences. But that's a different story. So the future research that these guys were talking about is that one of the weaknesses is that the current file sizes must be within a factor of 10. So if I have 100 lines in file A, that means I have to have under 1,000 lines in line B. Otherwise, it just doesn't make sense. One of the ways they were proposing to combat this was to take the larger file, break it up into equal-sized chunks, and then perform this distance on all those chunks and see which ones match, and then try to match and combine. Another thing they were trying to do is do a calculation based on the differences of neighborhood sizes, difference in compression ratios, difference in hashing algorithms. See, because currently they're using the Raven-Karp algorithms and hashing methodologies or some variant or adaptation of. They're talking about using some other stuff like MD5, SSA 512, that kind of stuff. So, hey, cool, great idea. That's where they're going with it. But my analysis of the situation is both good and bad. All right, the limitations here are still that you have a file size limitation. This thing is going to run on things that are less than about a gig. You're going to notice it if it's running on something that's 500 megs, because I tried. Did not work well. Documents of different sizes. So, once again, they stated it has to be within a factor of 10, right? And then also the general localization of the search patterns themselves tend to have an effect. Whether what you're searching for is at the beginning versus at the end, whether it's split into different locations, that's another thing. Also, there's plenty of other methods for combating the goals that they were trying to achieve. Well, not so much their stated goal, but the idea of being able to take two files from different locations and then try to match them and try to get some type of similarity. There's plenty of tools to combat this. We're not going to get into this because I really don't want to mention and teach anybody any other bad stuff, right? But once again, I put it down there. There's other tools to visually compare text. I'm going to show you one of those when I start doing some demonstrations. But the things that I love about this article is, man, the idea of hashing just never really struck me. I've thought about it before, but I never really went into it. The idea of being able to hash something with a velocity compression algorithm is basically, the idea here is you're getting a smaller version of the object that you're trying to analyze. This is specifically can be seen on a computer. This can be specifically seen in thumbnails, right? You can take a thumbnail of a picture, and when you're looking at your folder and you see 50 pictures, but they're the smaller version, you can't go from the smaller picture to the bigger picture, but you can go from the bigger picture to the smaller picture. That's something that had never really struck me before, right? This also gives us a way to get metadata on the files themselves, right? So, we can get the date the file was created, the last time it was accessed, the last time it was modified, the MAC stuff, modified access, create, all that. But this gives us more metadata, and data is always a good thing. And it's the secret sauce to artificial intelligence and machine learning. It's something we want more of. Is just data and metadata, more and more and more. Another advantage of this is the anonymous searching. It doesn't dawn on most of the general population about anonymity. The idea that I can't give up specific pieces of information is baffling in most circles. But the ability to anonymously search or offload the searching to somebody else is huge, especially in the anonymity part. So if I wanted to know if 50 people from company B stole the code from 10 people of company A, and I was hired as an outside investigator, all I would say is, hey, take this program right here. It gives me the hashes. I take the hashes from company A, take hashes from company B. I compare the two of them together and be like, hey, guess what? Company B's got a whole bunch of stuff from company A. Anyway. And I like the ability to adapt to other metrics, which is something that is listed in one of the later slides. All right, so the other areas of interest for myself is basically the idea of being able to fingerprint a file. All right, this was shown in the class itself in one of the tools called Hash My Files. We had to use Hash My Files to compare hashes. Great times. But the idea of being able to fingerprint a file, well, now we're adding more metadata to it. Now I can fingerprint it against other files and control files and that fun stuff. The other area of interest was a search, specifically in a kind of a steganographic search. I'll show that one in an example. So the first up was the fingerprint, file fingerprint, right? And this is a screen capture of the Hash My Files, where we see that it uses MD5 and SHA1, a CRC32, and so on and so forth. And we create this fingerprint because even if one of them fails, the likelihood of two of them failing in the same way is very low. And then when you combine it with the 5 that are on the screen, that's pretty much 0, right? But let's say we apply this to the concept of the Levenshtein distance itself. Well, there's more to just a Levenshtein distance. There's a Tomorrow Levenshtein distance, longest common subsequence, Hamming distance, Jaro-Winkler distance, cosine similarity. And if you were to combine all these together, like they did on the past slide here, which was where I have MD5, I have SHA1, 256, 512, 384. Well, what if we combined all these together and we did something like this, where we have file A and file B. We have all the information that was there before. Length of data and the length of the digest. We have the Levenshtein distance. We have the estimated Levenshtein distance. We have the significance score. We have the Tomorrow Levenshtein edit distance. We have the Jaro similarity, the Jaro-Winkler similarity, the Hamming distance, the Hamming distance of the digest, the Hamming distance of the data. We have the cosine similarity of the digest. We have the cosine similarity of the data. Those two in particular are really fun because you don't actually have to run them on the digest themselves. You can run them on the digest or the data because of the way that they operate. They can operate against large files in themselves. All right. Then you have things like the longest common subsequence, which is something else that can be used. You have file digest 1, file digest 2, file signature 1, file signature 2. And when you combine all this fun stuff together, you actually get something very similar to the fingerprint of the single file. And then you can do fingerprints on the single file or the comparison of the file or the comparison of a file to control file, and adding the ability to manipulate the variables in and of themselves to ensure uniqueness is an idea that is a fun idea, which deserves merit in future research. So finally, we get to the last slide, which sounds good, but, you know, it's not really because I've got demonstrations to do. All right. This is basically the list of the demonstrations that we're going to perform at the present moment in time because I wrote the code. So I figured I'd make you suffer through it. All right. So in this file, or in this folder, I have a whole bunch of Python because I program Python because, why not? All right. Anyway, first one, Levenshtein distance. All right. So the Python main, kill the caps lock, and this gives me my help in my list of stuff that I'm doing. Okay, cool. All right, so if we go back and we look at this and we say, I want to do the Levenshtein edit distance, and what's my first word? Word 1, I don't know. Well, it's something around me. Computer. And I need a second word. Word 2, Ferrari. Right? So this will tell me what the edit distance is that it takes, or the number of computations that it will take to take the word from computer to Ferrari. Press enter, we press go. And it says, hey man, it's going to take you 8 edits, whether they be addition, subtraction, or substitution to change the word computer to Ferrari. And somebody might be saying, hey, well, we need a little more proof that it's gonna be that. What about that matrix that you were showing us earlier? Okay, sure, why not? We'll throw the matrix in there too. And this is the matrix of what it would take to take the word computer to Ferrari. Let's do one for cat, and bat. So to take the word from cat to bat, we know that because it's small, it's just going to take the C to a B. And we can see that in the matrix here. It says I started out at 0, and I just want to change C to a B. That's 1. And it's 1 all the way down, and the last element is 1. Right? So let's try it again with something more fun. A, B, B, A, C, A, D, B, B, A, something. 2, word 2. Abracadabra. Purple monkey dishwasher. That didn't work. Well, let's try it again. Purple. Yeah, that makes sense. Can't use the same tag twice. Here we go. Wow. That's what it would take. It would take 23 edits to take the word abracadabra something to abracadabra purple monkey dishwasher. All right. So let us now go into the next one, which was the lossy compression algorithm they used to create the file signature and all of that greatness, right? We run it again. This tells me that I want to get the LCA. So I do my Python, and there. This basically is telling me that I have a list of files, and that all I need to do is go find one of these files, and I can perform the actions upon it. So let's go with search 1, control, which is number 3, right? And it shows me search 1 control, and the file size is 28.87 kilobytes, compression rate of 101. It has 29,566 characters. Here's the file digest, and here's the file signature. All right, let's do it again for something bigger. Yeah, not that big though. 37. Okay, it was smaller. All right. Now, what else do we have? We had a compare option, right? So let's look into the compare. Or let's actually go back. I can actually, with this tool that I created because I was bored, have the ability to change the compression rate as well as neighborhood size. So the compression rate is currently running at 101. Let's say I wanted a compression rate of 3, because that's going to end well. LAD dash. Here we go. Dash. No. Yeah, I hit the wrong button. Alright. Dash LCA dash compression of 3. Enter. Select my file. And let's say I wanted to do the, not that one, this one, right? So this one, with a compression of 3, the digest gets pretty large, right? And we used file selection 11, which was the XAV-1. As you can see, the length of the data read from the file digest, the compression rate, all that fun stuff. All right, let's go back and let's run this again. Well, no, kill that. I want to do compression rate of, I don't know, what's another prime number? 13 and 8 is 21. 21. All right, we'll go back to file 11, and you can see it shrank greatly. All right, but we also have the ability to do a compare. All right, so Python main -C. I want to compare 2 files. This is the starting point of where the authors, or this is the ending point of where the authors were. So if I wanted to compare files XAV XAB and XAB-1, I would do 10 and 11, and it does the comparison, and we can see the significance score, the estimated Levenshtein distance, all that fun greatness of everything that they did. Now we can continue on further, and let's say I wanted to do a compare, but I wanted to see all that cool stuff that you had put on the end, where you had shown us the Levenshtein distance, tomorrow Levenshtein distance, cosine similarity, Jaro-Winkler similarity, all that other fun stuff. We just add the dash F here, and we select 10 and 11 again, and wow, now I have all of the fingerprint that I was talking about earlier. Now, what is one of the things that we can do with this nice and wonderful information is that we can perform a search, right? I know that if I hash one file and I hash the other file and I find the hash of the second file in the first file, or the first file in the second file, that, hey, guess what? It's in there. So that's something we're interested in. Let's take a look and see if we have anything like that. Better yet, let's create it. All right, so we're going to go into our project and we're going to go into our test data. I don't know, let's pick one of these, XAC. I've never seen this guy before. We're going to call him, copy, paste. Here, I'll put it over so everybody can see it, right? And delete the copy. XAC, copy, paste. And I'm going to name him dash control, right? And I'm going to come up with another text file just out of the blue. New text document. I don't know. Bologna. Right? Let's open him up and add some beautiful bean characters. So we had all these characters. Alright. Take Control A, C, and now we've added a whole bunch of characters. Alright. So we take XAC control that we just created, XAC2 control. I don't know. We'll take him. We're going to take this guy, and we have the control, right? We're going to talk, and we're going to say, hey, I want this guy, and he's going to be search 1. Right? So we take, and let's open up search 1. All right. Now we take the stuff from Bologna, Control A, Control C, and we're going to go, I don't know, say about midway down this guy. Control V, save, right? So let's go back to our other window here, and let's say I want to get rid of this. What are my parameters for search? All right, Python of main dash S. All right, now I remember it was XAC, and I think we stole 2. So we'll say the first one is 22, and whoops, let's not do that. Okay, that's got to die. Okay, not sure how that happened. Let's try that again. Let's not try that again. Python main. No. Main.py-s. All right. Now that we're back, we're going to take the control, which was 22. And then we're going to take the XAC2, which was 19. Right? And it basically says, hey, I went through and I searched, and the digests matched. Right? Now, let's try this again. With the 22 is the control, 23 is the search. Try it again. 23, 22. It did not like that. But thankfully, I've got some extras. Let's try it again. This time we're going to start off with the search string of ZBA. And 44, which is where I'll find it. Compression digest length of 42-C. I'm going to alter the compression rate to, I don't know, 3 of the search string, which is 42 in 44. And it tells me that 100% of the search string was found in the search string where it was supposed to be found. So to make sure that I'm not just, pulling somebody's leg here, we'll go ahead and open up search string, right? It says that I'm a message from a bad guy. I am burying this message inside of a file. Let's go ahead and copy that. We're going to go ahead and search string found, right? Control F for find. I'm a message from bad guy. Find next. Hey, look, it's there, right? So let's go ahead and let's say we're going to take one of these other files, which was the XAC, right? Let's go ahead, Alt-V, open C project, so that everybody can see the screen. Test data. We're going to take XAC2, right? Control-C, Control-V. We're going to rename it to that because reasons. And we're going to open it with our Notepad++. Now, I'm going to go for my search string. Well, we're going to leave it alone first, all right? We're going to go back over here, and I want to say I have the search string, right? So we're going to search this again. First thing I'm going to select is my search string, which is number 42. And then I'm going to go to 47 here, which shouldn't have it. And it does not. All right? Now, we're going to take that search string, which is right here. We're going to add them to the end, just because I can. All right? And we're going to do it again, which was the 42 and 47. This time, he was found. So the idea here is that you can actually search inside of the documents to be able to find, and this really helps because, well, you can do it in all sorts of fun documents, but unfortunately, due to time limitations, I'm not going to run it on this one, but as you can see, some of these documents can get quite large. This one in particular is 832,000 lines long. And I believe I have others that are longer in here. Like this one that's going to take a while to open because it's really not heavy. Or maybe not. Anyway, so the idea here is that once again we can use these. We can use the hashing to search files, and it gets us into a very fun place. And that's the future idea that can be researched more. But unfortunately, I did not have enough time, energy, or other resources to pursue that. But in the meantime, this will suffice for the project at hand. Once again, my name is Juan Cota. Thank you for joining me for my final project for digital forensics, CSCI 554.01W. Thank you.